In this video, I'm going to be introducing some examples where we have to interpret rates of change, find out how we can use a derivative to solve a problem. So the derivative is a pretty abstract concept, and it can be used in a variety of fields. The derivative is representing a rate of change, and there are lots of things in the world that can be changing, increasing or decreasing, faster or slower, things like population or productions from a company, water flows, or any fluid flow, area and volume and motion of an object. They can all be moving around, increasing, decreasing, faster or slower. So we can use this idea of a derivative and apply it to a lot of different areas. So let's just do a few examples just to try and get an idea of how we can do that. In this first example, we're going to be dealing with temperature. Temperature can change. It can increase or decrease, faster or slower. So in this example, we're given the temperature function. So this function is representing the temperature at a given time, and lowercase t is going to represent our time in hours. So uppercase T is representing the temperature, lowercase t is representing the time that is going by as this food sits in a freezer. So we want to find the rate of change of our temperature, how fast or how slow our temperature is changing with respect to time. We want to do that for the following 4 times, and let's compare them. So the first thing we want to do, since we're finding a rate of change for this function, is find its derivative that represents its rate of change. I would rewrite that function, take that denominator up to the top and get rid of the fraction by using a negative exponent, and then we could just use our chain rule to derive this function. So to find the derivative, I'm going to take this exponent, multiply it by the coefficient at the front, and subtract 1 from that exponent. I'm going to keep my inside function the same and then multiply by the derivative of the inside function. So dropping -1 down and multiplying it with 700, we get -700. Keep the inside function the same and subtract 1 from our exponent. Excuse me. And then multiply by the derivative of the inside function. So the derivative of this is 2t plus 4. So we could keep it in that form. We could rewrite it a couple of different ways depending on how you want to work with it. But now that we got our derivative or our rate of change of our temperature, we're just going to plug some times into that function. So plugging 1 into our derivative function, we can simplify and round to 3 decimal places, and we get about -18.667, or approximately -19. So our temperature is decreasing 19 degrees per hour, or we're losing temperature 19 degrees per hour. If I want to find what our temperature rate was changing by at the end of the 3rd hour, I just plug 3 into our derivative function. Simplify and round to 3 decimal places, we get about -7.284. So our temperature is decreasing by about 7 degrees per hour at the end of the 3rd hour. So decreasing a little bit less. So the rate of change is decreasing. At the end of the 5th hour, I'm going to plug 5 into our derivative function, and we get about -3.240. So we're decreasing at about 3 degrees per hour at the end of the 5th hour. And then at the end of the 10th hour, if I plug 10 into the derivative function and simplify, we get about -7 or -0.747. So just shy of a degree loss per hour. So losing a lot of temperature at the end of the 1st hour, not so much temperature at the end of the 10th hour. We must be reaching our coldest point and remaining at that temperature somewhere after the 10th hour. And that seems to make sense. If something is stuck into the freezer, it's going to be losing its temperature, getting colder faster at first, and then as it reaches its coldest point, it would stop changing its temperature. Let's do another example with population. Population can increase or decrease. Let's talk about a population of 500 lions that's growing in number according to this function. And t is going to be used to measure time going by in years. So we can find the rate at which this population is changing or growing at the end of the 2nd year is what this is saying. So if we want to find the rate of change of this function, we want to find the derivative of this function, and then we'll find the rate of change when we plug 2 in for the t spot. So first, I would rewrite this function, make it a little bit easier to derive. I distributed 500 throughout, so 500 times 1 is 500, and 500 times 4t is 2000t, and then I took that denominator up to the top using a negative exponent. Now I don't have to deal with fractions, or I don't have to use the quotient rule, and I can just use the product rule to derive. So when I find the derivative of this function, the derivative of 500 is 0, so that just goes away. So I'm just focused on deriving these terms right here. So we got two functions being multiplied together. I'm going to derive that using the product rule. So when I find the derivative of the first function, it's 2000 times the original second function plus the original first function times the derivative of the second function. When I find the derivative of this, I need to use my chain rule. So I'm going to take -1 down to the front. I'm going to subtract 1 from the exponent, keep the inside function the same, and then multiply by the derivative of the inside. So -1 down to the front, keep the inside function the same, subtract 1 from my exponent, and then multiply by the derivative of the inside, which is 2t. I can then simplify a little bit. 2t times -1 times 2000t gives me -4000t squared. And then I can plug year values into this derivative function and find the rate at which the population is changing. So if we want to find the rate at which the population is changing at the end of the second year, I'm going to plug 2 into my derivative function and simplify, and we get about 31.55. So what does that represent? That's representing how the population of lions is changing at the end of the second year. So we could write a statement describing that. At the end of the second year, the population is increasing. We got a positive derivative result, and it's increasing by about 32 lions per year. Or if you don't like to round up when you're talking about organisms, you could say it's about 31. One more example, let's talk about the spread of a flu in a certain school. The spread is represented by this function, and the function is representing the total number of students infected. So this is representing the number of students who have the flu. T days after the flu was first noticed. So T is representing days. So this function is representing the number of students infected, and T is representing the number of days the infection is happening. So let's estimate the initial number of students infected with the flu. Well, an initial condition is whenever the variable equals 0. So when time is 0 at the start of this infection, how many students had the flu? So I'm just plugging 0 in for t into my original function to find the total number of students infected when t is 0. So by doing that and simplifying, we get about 4.743. You can say that's approximately 4 or 5 students were infected at the beginning. If we want to find how fast the flu is spreading after 3 days, we're finding the rate of change, or how much the flu is spreading and how fast. That's a rate of change. So we want to find the derivative of this function. I would rewrite that function first, just bringing that denominator up using a negative exponent. And then we can find the derivative using the chain rule. So using our chain rule, we're going to take that -1 down to the front, multiply it by 100, subtract 1 from that exponent, keep the inside function the same, and then multiply by the derivative of the inside function. To find the derivative of e cubed minus t, the derivative of that is itself times the derivative of the exponent. So the derivative of the exponent is -1. We can then simplify. -1 times -100 times e to the 3 minus t power gives me positive 100 e to the 3 minus t power times the quantity 1 plus e to the 3 minus t, all to the -2 power. So we could use that. That's our rate of change function, and we want to find out what the rate of change is after 3 days. So I plug 3 into my rate of change function, evaluate, and we get about 25. So that means that our flu is spreading at a rate of 25 students per day at the end of the 3rd day. One more question, when will the flu spread be its maximum rate? We'll find the maximum of this function. I would look at the graph, unless you want to find zeros of that derivative. Looking at the graph is a little bit easier. Looking at the graph of the original function, where is the slope the steepest? At about day 3. Or we could look at the graph of the derivative function and find the maximum rate, which happens when t is 3, or at the end of the 3rd day.